Hey everyone, and welcome back to another edition of The Explainer. Today we are strapping on our detective hats, molecular detective hats, that is. Picture this. Someone hands you a vial. It's a totally clear, completely invisible liquid, and they say, hey, draw me the exact chemical structure of this. Sounds literally impossible, right? Well, for an organic chemist, that's just a regular Tuesday. And it's all thanks to the ultimate forensic tool out there, nuclear magnetic resonance, or NMR spectroscopy. So in this explainer, we're going to unpack exactly how scientists decode this hidden molecular architecture using nothing but cold, hard chemical evidence. Let's get into it.
Okay, let's dive into this. The big question: how do we actually see what we literally cannot see? We can't exactly stick a molecule under a standard microscope and start pointing and counting hydrogen and carbon atoms. Doesn't work that way. Instead, we have to kind of interrogate the mystery molecule. We drop it into a massively powerful magnetic field and hit it with radio frequencies. This basically forces the atoms to report back on their immediate surroundings. The data they spit back out, that is our chemical evidence. And if we know how to read it, the molecule will basically confess its entire structure to us.
All right, here's our case file for today. We'll start with the molecular detective, then move into decoding chemical equivalents, explore the power of peak area, crunch the integration math, and finally, wrap it all up by solving the molecular mystery. Don't worry, we're going to move systematically from the core concepts right into the actionable math.
Number 1. The molecular detective. Let's look at the fundamental behavior of these atomic nuclei.
And this brilliantly illustrates the physics we're dealing with. On the left side, you've got a charged hydrogen nucleus, right? A proton. Now, because it has spin, it acts exactly like a tiny little magnet. Normally, without any outside interference, these tiny magnets point in totally random directions. It's chaos. But when we apply a strong external magnetic field, boom, they are forced to make a choice. Notice how the physical bar magnets on the right mirror this exact behavior. The nucleus can either align with the applied field, which is a nice, stable, lower energy state, or it can fight it, aligning against the field, which takes more work and puts it in a higher energy state. NMR spectroscopy essentially works by measuring the exact amount of energy it takes to flip these tiny atomic magnets from that comfortable low energy state to the high energy state.
Moving on to part 2, decoding chemical equivalents. Now we shift from looking at individual spins to looking at groups of protons. This is our first major clue.
So, chemical equivalents. This is absolutely crucial in NMR. By definition, we're talking about all the protons found in chemically identical environments within a molecule. I like to think of them as identical accomplices in our little mystery. Because they live in the exact same molecular neighborhood, maybe they're all attached to the exact same carbon atom that's spinning freely, they experience that magnetic field in the exact same way. So because of that identical experience, they exhibit the same chemical shift. Instead of giving us a bunch of separate, messy signals, they combine their voices and give us one single, unified signal on the spectrum.
Let's break down what this actually means for our visual evidence. Because equivalent protons act as a unified group, they resonate at a single, unique value. The cool consequence here is that distinct sets of protons will give you distinct peaks on the graph. This is a massive structural clue for us. It means if you simply count the number of peaks on an NMR spectrum, you instantly know exactly how many different types of protons exist in that molecule. You see 3 peaks? Boom! 3 distinct chemical environments. But, as you probably guessed, knowing the types of protons is really only half the battle.
Which brings us right into section 3, the power of peak area. This is where we translate those visual peaks into real, tangible measurements.
So, here is the million-dollar question for you. We know what types of protons are present now, but how on earth do we know how many there are in total? Counting the peaks gave us the number of unique proton neighborhoods, sure, but a neighborhood might be just one single proton hanging out alone on a branch, or it could be a whole bustling methyl group packed with 3 protons. How do we actually tell the difference just by glancing at a graph?
So the crucial point is this quote right here. The area under each peak is proportional to the number of hydrogens generating that peak. That right there is the absolute golden rule of NMR integration. We aren't just looking at how tall a peak is, right? We are measuring its entire footprint. A peak generated by 3 equivalent hydrogens is going to have 3 times the area of a peak generated by just 1 hydrogen. By measuring this area, we take those visual squiggles and translate them directly into hard, usable numbers. It is literally measuring the footprint of the evidence to solve the mystery.
Take a look at this. Here's what that raw visual evidence looks like on an NMR spectrum for a compound called benzyl acetate. You can clearly see the sharp peaks representing those different types of protons. But look a little closer at the data. To figure out the area under these peaks, the NMR spectrometer electronically integrates it for us. See that line? It traces a vertically rising path over each peak. The height that this integral line jumps is directly proportional to the area under the peak. It's basically a beautiful visual representation of calculus in action, and it gives us the exact proportions of our molecular accomplices.
All right, section 4, the integration math. Time to pick up the pace and turn that visual evidence into real proton counts.
Now, back in the day, on an older 60 MHz NMR chart, you would literally just count the grid divisions that the integral line rises. So for our benzyl acetate here, the first integral rises 55.5 divisions, the second is 22.0 divisions, the third is 32.5 divisions. But here's the catch. These numbers are purely relative. The spectrometer doesn't actually know there are exactly X amount of protons, it just knows the ratios of their areas. Telling another chemist, hey, I have 55.5 divisions of a proton is, well, totally useless. We have to massage this raw data to find the simplest whole number ratio.
To pull that off, we follow a super simple, foolproof 3-step method. Think of this as your trusty detective toolkit for NMR math. Step 1, you take all your raw integral numbers and divide them by whichever number is the absolute smallest. This smartly forces your smallest peak to equal exactly 1. Step 2, now, because molecules often have symmetry, your results from step 1 might end up as fractions, like 1.5 or 2.5. If that happens, you just multiply everything by 2 to clear the fraction and get whole numbers. And finally, step 3. We all know experimental data is never completely flawless, so you just round off your results to the nearest whole number to get your final, clean proton count.
Let's move to the next slide and see how this builds when we apply our 3 steps to modern digitized data, this time from a 300 MHz instrument. The computer spits out these digitized integral areas 4.58, 1.92, and 2.80. Following our toolkit, we divide all of them by the smallest value, which is 1.92. That gives us 2.39, 1.00, and 1.46. Now, since we have those pesky half numbers, we multiply the whole set by 2. This yields 4.78, 2.0, and 2.92. Finally, we just round them off, and the result, 5 hydrogens, 2 hydrogens, and 3 hydrogens, a beautiful, perfect 5-to-3 ratio. We've successfully taken raw, messy data and processed it into real, actionable intelligence.
Section 5, Solving the Molecular Mystery. This is the resolution phase where we bring the math and the chemical structure together.
Notice the integrated 300 MHz spectrum of benzyl acetate we have here. Based on our step-by-step math, we know for a fact that peaks correspond to a 5-to-2-to-3 ratio of protons. And if you actually look at the structure of benzyl acetate, it has exactly 3 groups of protons, 5 sitting on a benzene ring, 2 on a methylene group, and 3 over on a methyl group. It's so satisfying, right? The calculated math maps onto the physical reality flawlessly.
Now, what's really interesting about this slide is how it highlights the dual power of NMR. Check out this comparison. On one side, we have 5 aromatic protons. Because they live on that specialized ring, their chemical environment shifts their signal way down to 7.3 parts per million on the chart. On the flip side, the 3 methyl protons are in a totally different environment, so they show up at 2.0 parts per million. The chemical shift tells us exactly what the structure looks like, but the integral area tells us exactly how much of it there is. It's a brilliant combo.
And that brings us to a highly satisfying conclusion for our case file today. When we add up our calculated, rounded integral values, 5 plus 2 plus 3, we get 10 protons in total. And guess what? The actual chemical formula for benzyl acetate is C9H10O2, 10 protons. The math perfectly matches the blueprint by combining the number of peaks, the position of the peaks, and crucially, the integrated area under those peaks. Our invisible molecule has been completely unmasked.
We've seen how elegant and precise this is for a small 10-proton molecule, but I want to leave you with this provocative thought. If we can decode the exact blueprint of a 10-proton molecule so elegantly, how does this integration tool scale to massive, complex pharmaceutical compounds? Imagine analyzing drugs with dozens or even hundreds of protons. The foundational rules of peak area and chemical equivalents that you've just seen are the exact same ones used to discover life-saving drugs in modern labs every single day. The tool is the same. The mystery just gets bigger. Thank you so much for joining me on this explainer. Keep asking questions, keep studying the data, and I'll catch you in the next one.